Quantum electrodynamics and the photovoltaic effect, a fundamental relationship. The photovoltaic effect, which forms the basis of solar energy technology, is a process that involves the conversion of light energy into electrical energy within certain materials, predominantly semiconductors. This remarkable phenomenon is intrinsically tied to the principles of quantum electrodynamics, or QED, a fundamental theory that describes the interactions between light and matter at the quantum level. This intricate relationship between QED and the photovoltaic effect, elucidating the quantum mechanical processes that underpin the generation of electrical current from sunlight. By bridging the gap between theoretical physics and practical applications, quantum electrodynamics play a pivotal role in enabling and optimizing the photovoltaic effect. The journey for sustainable energy sources has been the institutional force behind numerous technological advancements, with solar energy emerging as an integral solution to meeting the needs of global energy demand. At the heart of this technology lies the photovoltaic effect, a phenomenon that enables the conversion of light energy into electrical energy within certain materials, primarily semiconductors. While the practical applications of this effect are well established, the fundamental principles that govern its operation are rooted in the realm of quantum mechanics, specifically in the theory of quantum electrodynamics. QED, a cornerstone of modern physics, provides an all-around theoretical framework for understanding the interactions between light and matter at the quantum level. By unraveling the intricacies of these interactions, QED offers insights into the photovoltaic process, paving the way for the optimization and advancement of solar cell technology. The photovoltaic process begins with the absorption of photons from sunlight by the semiconductor material, typically silicon. QED describes this crucial initiating event by quantifying the probability of photon absorption and the subsequent excitation of electrons to higher energy states within the semiconductor's electronic band structure. According to QED, photons are quantized packets of electromagnetic radiation that possess both wave-like and particle-like properties. When a photon with sufficient energy encounters an electron in the semiconductor's valence band, it can impart its energy to the electron, promoting it to the conduction band. This excitation process is governed by the principles of quantum mechanics, and QED provides the theoretical framework for calculating the probability of such transitions occurring. The absorption of photons is a fundamental step in the photovoltaic process, as it sets in motion a series of subsequent events that ultimately lead to the generation of electrical current. Quantum electrodynamics not only explains the absorption process but also offers insights into the optimal design of semiconductor materials to enhance their light-absorbing capabilities, thereby increasing the overall efficiency of solar cells. When a photon is absorbed, and an electron is promoted to the conduction band, a positively charged hole is left behind in the valence band. These electron-hole pairs, created through the absorption of photons, are the driving force behind the generation of electrical current in solar cells. QED provides a comprehensive understanding of the behavior and properties of these electron-hole pairs, which are essentially quantum mechanical quasi-particles. The theory describes how these charged particles interact with the semiconductor lattice, as well as with any impurities or defects present in the material. Additionally, QED elucidates the processes by which electron-hole pairs can recombine, releasing their energy in the form of heat or light, photons. The ability to accurately model and predict the behavior of electron-hole pairs is crucial for optimizing the efficiency of solar cells. Quantum electrodynamics-based calculations aid in the design of semiconductor materials and device architectures that can maximize the separation and transport of these charge carriers. This minimizes recombination losses and enhancing the overall performance of the photovoltaic system. Charge separation and transport. Once electron-hole pairs are generated within the semiconductor, they must be efficiently separated and transported to the opposite electrodes of the solar cell to create an electrical current. The theory explains the behavior of charged particles, such as electrons and holes, in the presence of electric and magnetic fields, as well as their interactions with the semiconductor lattice and any impurities or defects present. These interactions can significantly impact the mobility and lifetime of charge carriers. ultimately affecting the efficiency of charge separation and transport. By leveraging the principles of quantum electrodynamics, researchers and engineers can design semiconductor materials and device architectures that facilitate efficient charge separation and transport. This includes the incorporation of built-in electric fields, the introduction of charge-selective contacts, and the optimization of material properties to minimize carrier recombination and enhance charge collection. While the generation and separation of electron-hole pairs are essential for the photovoltaic effect, undesired recombination processes can occur, leading to energy losses and reduced efficiency. QED provides insights into these recombination mechanisms, enabling strategies to mitigate their impact. Recombination processes can occur through various pathways, such as radiative recombination, where electron-hole pairs recombine and release their energy in the form of photons, or non-radiative recombination, where the energy is dissipated as heat. QED describes these processes at the quantum level, allowing for the calculation of recombination rates and the identification of factors that influence them. By understanding the recombination mechanisms through the lens of quantum electrodynamics, researchers can design semiconductor materials and device architectures that minimize these losses. This can involve techniques such as passivation of defects, optimization of doping profiles, and the incorporation of advanced device structures that suppress recombination pathways. The photovoltaic effect, the cornerstone of solar cell technology, is intrinsically linked to the principles of quantum electrodynamics, QED. This fundamental theory provides a framework for understanding the interactions between light and matter at the quantum level, elucidating the processes that govern the conversion of light energy into electrical energy within semiconductor materials. From the absorption of photons and the creation of electron-hole pairs to the separation and transport of charges, and the mitigation of recombination losses, QED offers insights and quantitative models that guide the design and optimization of photovoltaic devices. By bridging the gap between theoretical physics and practical applications, QED paves the way for advancements in solar cell technology. As the demand for sustainable energy sources continues to grow, the synergy between QED and the photovoltaic effect will remain a focal point for researchers and engineers alike. Through ongoing theoretical research, experimental development, and practical application, these principles will play a crucial role in pushing the boundaries of solar cell efficiency, enabling the development of increasingly cost-effective and high-performance photovoltaic systems.